Hello everyone, my name is Yogesh Ihapunia, and today in this episode we shall be discussing some new concepts of the world of electrostatics. If you remember, in the past episodes what we have discussed was the concept of electric field lines, and then we discussed the concept of electric flux. We also discussed that suppose I have a charge and I have got some planar cross sectional area. So the electric field lines coming out of that charge depends upon the orientation of that planar cross section area that I am taking into consideration. If I tilt it like this, that will be different. Tilt it like this, that will be different. Like this, the things are going to be really different. But this is not the case always. Can you imagine that there are always single charges present around you? No. There must be something that is called the two charges that are always remaining together, just like say two best friends, two brothers. So we have to ponder over these thoughts, how these two charges remain with each other and how do they affect the surroundings that they are interacting with. So today we will discuss a very good concept of electrostatics, that is the concept of electric dipoles. So what is an electric dipole exactly? An electric dipole is something like, if I have got, see, if this is my finger, so if I can place two charges, that is one charge here and one charge here, it will make it a dipole. Is that the case? Well, exactly not. Just imagine you are in a birthday party of your friend and you are playing a game. You have got a straw and you have got two balloons. One balloon is a smaller one. You simply blow some air and say suppose it is this much. And you have got some bigger balloon in which you store some candies. So, and if you attach these two balloons with some straw that you are holding, how it look like? The bigger balloon will simply try to go down and the smaller one will feel helpless. Well, physics says everything has to be balanced. So this concept of dipoles is nothing but we have got two charges and they are connected by say some invisible string. What we say is that they are connected by some sort of distance between them, and we have two charges. But what about the magnitude of them? Well, the magnitude has to be equal, because you know the basic law of this world is the law of equilibrium. Everything has to be in equilibrium. So according to this law of equilibrium, the nature said the two dipoles has to be of equal magnitude, and so they are. Now how will they affect each other, or how will they interact with any point residing in their surroundings? That is a very interesting question, because so far what we have discussed is that we have got a charge and we will say suppose there are 5 charges around here, and these 5 charges will have some sort of force over them. But in the case of dipoles, we have got a point here and we have got a dipole here. So how this dipole will interact with this point is really of very big importance. So for this we'll do a very simple activity and we'll find out how the dipoles will affect the points in their surroundings. To understand this concept, let us take this pen into consideration and think as if it's a dipole. I take this tip as some positive charge and this bigger one as some negative charge. Now before proceeding further, I would like to tell you one more thing, that following the law of equilibria, there is a very good nature, or there is a very good property of this dipole. The total charge on this dipole is always 0. That is this plus 1, then it will be minus 1. If it is plus 2, it will be minus 2. Oh, I just forgot the unit, it's q. So if it is plus q, this is minus q. Plus 2q, this is minus 2q. So we know what is a dipole, what is the total charge over it. I have got something in its surrounding, say suppose this cap. So if I say that it is some sort of test charge, so what's the test charge? Yes, you're right, test charge is something that is really infinitely small as compared to the charge that we are taking into consideration, but has got a larger impact over the properties of it. this is a test charge, say suppose half q or anything you like. So this positive charge will definitely have some sort of repulsion on this positive test charge. But we also have what? A negative charge here. With the positive repulsion, that is this positive charge is giving, this point is also having, or this charge is also having some sort of attraction that is due to this negative charge. If I draw this on a sheet of paper, what I will see that there is some, say, positive charge around here, and there is, say, some a negative charge around here, and I have got a test charge here. If I draw it really very roughly, what will happen is that this positive charge will try to repel it, likewise here. So what will happen? This positive charge is repelling it, so the force of repulsion will be just like this. It will go in this way. It will try to push it further. Don't come into my territory. But it has also got a friend, and the friend is that this negative charge. It will say, you are welcome in my home, please come, like this. So if I draw it here, what will I see is that the electric field lines is like this. This electric field that is pushing it towards. Why I said electric field lines is all that you all know. The force is only due to the electric field, and electric field is due to the electric field lines. And what we discussed was that the whole world of electrostatics is only dependent upon the electric field lines. And if I consider about this one, it will be in this direction. I call it E1 and I call it E2. This is how the dipole will interact in the presence of some point in its surrounding, depending upon whether the test charge is something plus q or minus q or of that singular order. The orientation or the direction of the force will differ. But there is a word of caution. A lot of people think that dipoles means an arrangement where the magnitude of the two charges is equal. But we have to know that the total charge on a dipole has to be 0. So you can't have two positive charges or two negative charges on a dipole. They has to be different. That is, they have to be opposite. So the definition goes like this: an arrangement of equal and oppositely charged particles or charges which are separated by a certain distance forms a dipole whose total charge is 0 and who affects the test charge in its surrounding depending upon the orientation or the direction of the force that happens there. Now, since we have discussed that what exactly a dipole is and how it will affect the point charge lying around it, we shall move further and see the situation that suppose I have a dipole and I keep it in some external field like this. So when this is a dipole and I have got some external field that I will designate by this pen, what will happen is, say suppose this is the electric field going in this direction, and I have a dipole that I have kept with my affirmation in this direction. Now, if the electric field has got some attraction for the positive charge, that is this end, and some repulsion for the negative charge, that is this end, what will happen? Just observe really very carefully. What we have done is, this is the positive end and this is the negative end. Yes, the electric field is in this direction. Now, when it is placed here, it will simply try to go nearer to it. Since the positive charge is being attracted or is being given some special treatment by this electric field, it will try to rotate. And when it rotates, that means a very singular thing. That is, in the presence of electric field, that is this dipole, and this electric field plays a very crucial role. How? This electric field will simply affect the positive side of the dipole to get attracted and the negative side of the dipole to be, what do you call? Yes, to be rejected. This gives rise to a thing called, that we know in our day-to-day life, that is torque. You must have seen bus drivers or even anyone driving the car. What they will do is, they will have got a steering like this, and they will try to rotate it further like this. You can take that thing as an example of the dipoles. That is, your two hands are some sort of charges, and that steering is the distance separating you. Suppose you are about to turn and then you turn it like this. When you turned it, what will happen is that after some time you will come on a straight road, so then you will leave it. So what will happen? It will just come like this. Just see, you have turned it like this, but after some time it will try to come in its initial position. And what will you say about it? You will say, no, this is the tendency of the steering to come into the initial position. Well, actually this is the tendency of nearly all the things that we encounter in our day-to-day life and the charges that are around us. Everybody wants to be in a state of equilibrium. For example, if I go with the example of this electric field and the dipole, with the electric field in this direction and the dipole here, while I am experiencing while I am seeing that this dipole is being attracted by the electric field, that is this positive end, and rejected by this negative end, but I am seeing that a sort of force is happening. Some force is driving this electric dipole in the direction of electric field. That force is known as torque, and torque is really very important. That is, if we do not consider torque while we are discussing the dipoles in some external field, I think we are missing a very important property of dipoles, because a torque is always responsible to keep the dipoles in the alignment or with the field. That is, if the field is say upward direction, the torque will try and maintain the direction of the dipole or the alignment of the dipole with the electric field E. And this you can easily see in the steering of cars, buses, trucks, everywhere. They will try to be in a state of equilibrium with the current position being the simpler one, and when you rotate it, it will come back to its own. Now, since we have discussed what exactly are dipoles and how a point residing in the neighborhood of a dipole will experience the field or the force, and we have also discussed that if I place a dipole in some external field, how it will react, that is, some torque will act and will try to align the dipole with the electric field there. But we must be thinking that okay, this is all dipoles. I know what a dipole is, how it reacts to some certain situations, like some point residing in surrounding or something like that. But what exactly is the physical significance of dipoles? Because if we are discussing dipoles here, then there must be something that we can find in our day-to-day life that is really very important. Actually, the concept of dipoles is really very important in understanding the behavior of certain molecules. Like if you take certain molecules, and what they have got is, they have got the positive charge and the negative charge. Do you know the formula of H2O? Yeah, that same H2O. Yeah, what happens is, the thing that matters in case of the molecules is that the where the positive charges, that is the center of the positive charge and the negative charges, they are placed. If I have got some positive charge center and the negative charge center aligned at the same place, what will I see is that the net dipole moment is 0, and if I place the absence of some electric field, there will be no dipole moment. If I take some other example, that is what I mentioned just right now, H2O, or if I take say carbon dioxide, CO2, the centers of positive charges and the negative charges, they don't align at the same place. They are a bit slightly, they do not agree with each other, and they say I will remain here, you remain here. And even if there is no electric field, they will have some sort of dipole moment. Okay, you don't agree with me? I have got a very good example for you. You must be thinking, what does it mean by the center of positive and negative charges aligning? Take the example of this pen. This is the positive charge and this is the negative charge. So they are aligned in the same plane, means if I have a scale, so what I will see is that the center of negative charge and the center of positive charge are in a same line, that is, one is just behind other. So, this is some sort of what you call your neutral dipole. Even if there is an electric field, it will try to rotate, but if there is no electric field, it will remain as it is. But if I take some molecule, say H2O, so this will be the case, but there will be some slight orientation. The positive charge will remain here and the negative one will remain here. See, the difference is here. They are not aligning in the same plane. So, even if there is no electric field around them, or if I place them in the absence of electric field, they will have some net dipole moment. Where do you find the application of this? I leave it to you, because I can only give you a hint. You all must be seen the microwaves. So, just go through the things and find it out how the microwave will heat some things for us. You want to make a Maggi, it will heat for you. But the concept of heating of that molecule of water in that bowl that you have taken into consideration depends upon the concept of dipole. So, what we have discussed today? We have discussed about what exactly are dipoles. They are electrically neutral molecules of two equal and opposite charges separated by a distance. When they are brought in contact with some test charge in their surrounding, they affect it in their own way. We also discussed the notion of torque, that if I place some dipole in the some of the electric field that I am taking into consideration, they will bend a bit, they will try to align with the electric field around them. And then I discussed about the physical significance of dipoles, that what is the if the center of positive charge and the negative charge align at the same place, and what if they don't align. So, in the next coming episode, we shall be discussing about the configuration of charges, means how a charge is distributed along a whole layer, say suppose of a thread or of a plane, etc. like this. Till then, take care of you, and please don't wait till to ponder the world of physics. Thank you.